Hello, good evening everyone. I welcome all of you to the most comprehensive exam preparation app, that is BYJU'S app. All of you are welcome here. So today we have a fantastic session on strength-of-material. That topic is for step bar and temperature stress. This is one of the important topic for the GATE perspective. So the students, those who are going to appear for the GATE examination, it will be one of the most convenient and important topics. So all of you please join fast. All of you please join fast so that we can start our session. And please do not forget to share and like the session. Please do not forget to share and like the session. All of you please join fast and share with your friends. Let us start with the topic now. This is my small introduction, and those who want to connect with me, they can join me on Telegram channel, that is Civil by Ansari sir. These are the star faculty of the BYJU'S Prep for the civil department, and there are several programs going on like Vision for GATE 2022, that rank up GATE for Vision 2022, that is also for GATE 2023 aspirants. So you can join according to your interest. The deformation of axial bar. If you see the deformation of axial bar, you all know that if you have a bar applied with the axial force, what will happen? The deformation we are calculating with the help of the formula, which is nothing but PL by A, that everyone knows, and the body is under equilibrium. Now, if you have a different length of the bar associated or connected together, what will happen now? If you have a different length of the bar connected together, if I'll ask you what is the final deformation of the structure, all the three bar are connected with each other, and if I'll ask you what is the deformation, total deformation, what will be that? You all know that the individual deformation we are calculating based on our method of superposition, the individual deformations we are calculating and then we are adding it up, right? As you can see that there is only one force it is acting at this location. So for all the bar, only same P force will be applied, and individual deformation for the bar L1 length, then individual deformation for the bar L2 length, and the individual deformation for the bar L3 length will be added together to know the final deformation of the total bar. We are applying the method of superposition to get that. So simply the total deformation of individual will be added. Now suppose instead of the length, if the cross section will get varied, if there is a variation of the cross section, then what will happen? Of course, once again you are going to draw the free body diagram for each and individual bar, isn't it? Suppose for the L1, what is the force which is going to act over the L1? Of course, here in this particular diagram only one force is acting throughout. So line of action of the force, if you'll see, for all the bars are having same line of action of the force. If you'll go through it, P force is acting for all the bars, so you can apply P force to this bar. Similarly, you can apply same force, and similarly you can apply the same force for the bar which is acting over this particular bar. So draw the free body diagram, apply the individual force which is acting on the bar, then calculate the individual deformation. At this particular moment you can see that the area is varying. If the cross-sectional area is varying, of course, once again same formula you will utilize by putting this particular or corresponding cross-sectional area for the, like for this particular bar it has maybe L1 length and cross-sectional area A1. For this bar the length is maybe L2 and the cross-sectional area is A2, and for this bar the length is maybe L3 and the cross-section area is A3. Now other than that, what are the steps you need to get involved? See, this is the kind of problem which will generally use to appear for different type of examination, and especially for the GATE also. Suppose this is the one problem which is there in front of you. Few loads are acting and this structure is under static equilibrium. If the structure is said that it is under static equilibrium, if the whole structure is under static equilibrium, there are only axial forces acting on these bars at different location. Now, all the forces, whatever the forces are acting on this particular structure, if you can see, only the axial forces are there. What is the meaning of equilibrium of this structure? So the whole structure is neither moving towards right side nor moving towards left side. If the structure is under equilibrium, the individual component also must be under equilibrium. So we will draw the free body diagram for each and every element. But at the same time, you can see that the force P is not also known. It is unknown. So for this type of problem, what will be your approach? So the first approach will be use the equilibrium equation to find the unknown. So the unknown force, wherever it will be there. Though I have given it here, it will be anywhere. That unknown force you can calculate with the help of the axial, that equilibrium equation. What is that equilibrium equation you are going to use? That is summation of fx equal to 0. Summation of fx equal to 0. And by using that summation of fx equal to 0, you will find the value of P. Then what will be the next step? You will split it, you will split the bar and you will draw the free body diagram for individual bar. Then next step, you will calculate the individual deformation for each and every bar and you will add all those according to their sign. If they are doing elongation, maybe you can take the elongation as positive, or maybe if they are contracting, you can consider it as a negative. With their sign, just you will add all the deformations, that's all. So take one bar here. While doing so, first of all, you are going to find out what is the force P. Now, after application of your summation of fx equal to 0, you can see that right side forces, if I will consider as plus, maybe, so that P plus 3 plus 8 minus of 15 must be equal to 0. And from here you will get P equals to how much you will get? 15 minus 11, that is 4. So P value, I got it, that is nothing but 4. Now take individual P's, and here is the key to solve this type of problem. Just you do one thing. Whenever you are taking any of the particular element, you stand at the center. By standing at the center, you see either towards left side or towards right side. Either you see towards left side or you see towards right side. Suppose if I'll see towards left side, why I am doing so? Because if I'm considering this particular element, see, whole structure is under static equilibrium. So the piece is also under static equilibrium. So whatever the forces are acting towards left side must be equal to the right side. Then only this piece will be said as under static equilibrium, isn't it? So that is why I am saying that add all the forces towards either left side or all the forces towards left side. That's all. Now considering that the left side I have only one force, so I'll be adding this, this 15 will be there, that's all. So 15 kilonewton is acting at this particular block. So stand at the center first of all. Stand at the center and you see what is the force acting on the left side for this particular block which is having length L1. The force which is acting here is nothing but 15. You must consider the unit also, which is 15 kilonewton, you can say that. Now if it is 15, the other side you don't have to worry at all. You apply 15 without any hesitation, because if it is under static equilibrium, it must be 15 only. Then you take the another element which is having the length L2. For the L2, once again stand at the center. Delete this one. Now stand at the center of this block. By standing at the center of the block, either you add left side forces or you add right side forces. Suppose if I'm adding maybe anyone, right side forces. P is already, we have calculated 4 plus 3 both are acting in the same direction, that is 7. So this block is under force 7 kilonewton towards this side. You don't have to worry. This side you simply apply to the opposite direction, because it has to be under static equilibrium. It must be 7. You got the right side force summation of forces at 7 kilonewton. So this side you, without any hesitation, you provide 7 kilonewton. That's all. Take the another block. While taking the another block, once again you stand at the center. You stand at the center. By standing at center, you add all the forces either towards right side or towards left side of the considered section. Now, if I'll add towards right side, because I have a less force here, I will add all the right side forces, which is nothing but 4, which is acting at this particular block. So 4 kilonewton is acting here. Without any hesitation, I will apply equal and opposite side force. Because this block is under static equilibrium, it must be there. Both must be same and acting opposite to each other. So this is 4 kilonewton. Now, once you have drawn the free body diagram, the next step is simply you need to calculate the individual deformation. So the individual deformation can be calculated by using the formula PL by AE. That's all. Whatever the length is at, P1 L1 by A1 E1. For this one, P2 L2 by A2 E2. Then for this one, P3 L3 by A3 E3. Although for this particular type of problem, cross-sectional area is same, so you can put whatever the value you have. Based on that, all of them are actually tensile and elongating, so all of them I will put it as plus. Suppose if one of the block is going to get contracted due to some compressive force, if you have a contraction, then of course I am going to use the negative sign for that one. If you have any doubt till this problem, you please tell me, otherwise we'll move forward. And at the same time, please do not forget to share. Please do not forget to share. Now consider one more example here. Suppose this is the kind of example. Here, to find out the force P, what we'll do? Summation of all the forces in x direction. Summation of all the forces in x direction must be equal to 0. That is their equilibrium equation, isn't it? So all this, suppose right side forces, right side acting forces, if I'll consider as plus, so 4 plus P, see, 4 plus P and plus 4. What it will be? 4 plus P plus 4. Then minus of 8 minus of 2. That's all. Must be equal to 0. And from here I'll get P value equals to 2. Then individual, just consider individual block for drawing of free body diagram. Maybe if you'll consider the block A first. Block A. For the block A, just stand at the center and try to see. The 8 kilonewton is acting. 8 kilonewton. If you see towards left side, 8 kilonewton is acting. Right side, you apply the same 8 kilonewton without any hesitation. For the block B, this is for the block A. Draw it for the block B. If you draw it for the block B, stand once again at the center. Once again at the center. Either you see towards left side or towards right side. That's all. So left side, if I'll see that 8 kilonewton is acting towards that side, 4 is acting towards inner side. So you will be finding out the resultant, which is acting 4 kilonewton. That is 8 minus 4. 4 kilonewton. 8 minus 4, which is acting towards this side for the block B. Once you have added this one, for other side, you don't have to worry. Do not add it. Simply you apply 4 kilonewton, because if the whole structure is under static equilibrium, it must be 4 only. Then for the another block, draw the free body diagram. Stand at the center. Take this block out. That is the block C. Taking the block C out, add all the forces. Of course, right side I have a lesser force, so I'll add all the right side forces, which is 4 minus 2. So it is actually under 2 kilonewton. So left side also I'll apply same 2 kilonewton without any hesitation. Then for the block D, of course, it is subjected to 4 kilonewton this side, which you can see by standing at the center, this 4 kilonewton. Then same 4 kilonewton will be applied here. That's all. This is the free body diagram of your individual blocks. Once you have drawn the free body diagram for individual block, next thing is that simply, for each and every block, whatever the forces you have, based on that, calculate the individual deformation. Based on their nature. The nature is that it is going to get elongate, so plus elongation plus elongation plus elongation plus. Fortunately, I have all the elongation. If I have some contraction, then I'll be using that negative sign, isn't it? If I have somewhere in the block, if I have a compressive force is acting, then I'll be using that negative sign. Then what is the final one? Add all this to find the final delta. So final delta can be calculated as delta is delta of L1 plus delta of L2 plus delta of L3 plus delta of L4. Did you get that? Next one. This is one of the problem, you can just solve it. This is one of the problem, you can solve it. How to solve this problem? Find the total deflection. What will be the total deflection here? For finding out the total deflection, once again I'll say that we will find out first of all we'll draw the free body diagram here, isn't it? So draw the free body diagram for individual block. Draw the free body diagram for individual block. This is the first one. If you'll stand at the center, you see that what are the forces acting, summation of all the forces to any one side. So if I'll see the summation of forces towards right side, 2p is acting leftward direction, p is acting in right side direction. So finally I'll get a p force, 2p minus p. The resultant p will be acting here. Other side, of course, without any hesitation I will apply, because it is under static equilibrium, and hence it must be under static equilibrium, and for that other side you will get the p force. That's all. The middle one, if you draw the free body diagram, what are the forces acting here? If you stand at the center, you will find that a 2p is acting here and 2p is in compressive in nature. So that's all. 2p is acting towards this side and 2p is acting, of course, once you will get the 2p from this side, you don't have to worry. From other side also you apply 2p force in opposite nature, because the block must be under static equilibrium. The bigger one, the last one if you draw here, you'll find that stand at the center, 2p is acting, that's all. So from other side, don't have to worry, apply 2p, same 2p will be there, that's all. Summation of all the forces I have seen towards any one side. Now individual deformation, if you find it out, this length has not been given, so you consider all the block has the same length, only the cross-sectional area are different for each and every one. So PL by A, if you do here, this is 2A is the cross-section, here A is the cross-section, here 3A is the cross-section. So individual deformation, if you find it out here, how much you are going to get, that is PL by AE, that is 2AE. Then for this one, P, it is 2PL by AE, and of course all of them are negative. Why? Because all of them are going to get contracted, isn't it? All of them are going to get contracted. So that is negative. Then PL by AE, that is 2PL by AE, and for this one, once again it is having a contraction, so minus of 2PL by AE, 3AE. What will be the final deformation? So final deformation will be all are having contraction. I'll take the minus sign as a common one, and you'll find PL, or of course PL by AE also can be taken as a common, no problem at all. PL by AE, and finally you have half plus 2 plus 2 by 3. If you'll add all of them, how much you'll get? You are getting 19 by 6, na? 19 by 6. I think there is some problem here. I think it must be 19. 19 by 6 under compression. Now, what about the temperature stress? What about the temperature stress? How to deal with the temperature stress problem? See, first of all, if you have any block, suppose a cantilever beam you have, if you are going to increase the temperature, you know that the block is going to get extended. No? There will be expansion. If you don't have any restraining position, a free expansion will be there for the block. And alpha is the property of the material which we are defining as a coefficient of thermal change. What is the definition of alpha first of all? What is the definition of alpha? For the alpha of concrete and steel, you know that it is same, but what is the definition for alpha? It is nothing but the temperature rising. If you're rising the temperature or increasing the temperature by 1 degree centigrade, for the 1 mm of steel, the change in length will be 12 into 10 to the minus 6 mm. Means if I'm saying that alpha of steel, some value alpha, for the rise of 1 degree centigrade, for the unit length of the material, it will be having change in length alpha. So alpha is nothing but change in length of the material due to unit degree rise of temperature. Alpha is nothing but change in length of your material having unit length due to rise of 1 degree centigrade temperature. And you know that alpha of concrete and steel are same, that is why they are compatible also. If you rise the temperature, there will be no temperature stress between the bondage of steel and concrete. Now, if you are rising the temperature by T degree centigrade for the L length of the material, what will happen? If you have a material having L length and you are rising the temperature by T degree centigrade, of course, alpha is what? If you are rising the temperature by 1 degree centigrade for the material of 1 mm, that value you are calling it as alpha. This is alpha for steel. If you are rising the temperature by T degree centigrade, the change in length will be alpha T, and though if you are rising the temperature for L length, it will be alpha LT, alpha TL or alpha LT, isn't it? Alpha LT. This is the free expansion. This is the free expansion of your bar due to the rise of temperature T degree centigrade. Now suppose instead of that, if you have a restraint, then what will happen? This type of restraint, if you are restricting it from both sides, if your bar is now fixed. Now if you are going to increase the temperature by T degree centigrade, what will happen? Of course, these restrained position will not allow your bar to get expand, isn't it? Then a compressive force will generate. Or maybe if it is restrained, it is fixed, and if you are reducing the temperature, the bar will try to contract, and the restraining position or fixed position will not allow the bar to get contracted, and a tensile force will generate. So the tensile or compressive force will generate based on the whether you are rising the temperature or whether you are lowering down the temperature. Suppose if you are rising the temperature, what will happen? Of course, the bar will not be able to expand, and a compressive force will get generated. Now, how to analyze this type of question? What will be the force? How to calculate the force for the bar? Let us see the simplest approach for that one, for the temperature stress. Suppose a bar is restrained at both the position, or I can say that a bar is fixed. A bar of length L is fixed from both sides. First of all, you do one thing, remove one of the support. By removing one of the support, you allow this bar for the free expansion. Rise the temperature by T degree centigrade. Rise the temperature by T degree centigrade and allow it for the free expansion, and then find the free expansion. See it as a delta 1. This is the free expansion you have now due to the rise of T degree centigrade, alpha LT. The next step, you apply the force. Although I don't know what is the amount of the force. Apply the force P maybe, and try to compress it by the force P, and say that one as a delta 2. Acha, that force, by applying that force, either you can bring back this bar to the same initial position, or you can stop it somewhere here also, no problem. You have always a choice that whether you want to bring it back to the same initial position or you want to get it stopped anywhere. But with this storyline, you can solve all the type of problem. So then you apply the force, bring it back according to your requirement. Suppose if I am applying the force, I am not bringing it back to the initial position, I am just keeping it at somewhere in between. So due to the application of the force, I am bringing it back to some in between position. Did you get that? Now suppose after application of the force, your bar is at this location. Say this is as delta 2. So free expansion was your delta 1, and the contraction due to the application of the force on your axial bar was delta 2. If you are applying the P force for any bar having a length L, you can always apply the formula that is PL by A. Although you can ask me one more thing, that's that instead of using that PL by A, you would have used that PL plus whatever the delta 1 you have here, isn't it? Because the initial length was L plus delta 1, isn't it? So of course I'll say that this delta 1 we have ignored because of small value, that's all. Now this delta 2 is nothing but PL by A, which you are applying the force. Now apply the compatibility condition. What is that compatibility condition? Says that the deformation delta 1 minus delta 2 must be equals to the remaining one. This is delta 1. Suppose that it was the expansion, I will consider it as a plus 1. Delta 2 was a contraction, so I have considered as -1. And final delta, which one is the final delta? This is your final delta. This will be your final delta. It may be of any value. If you are bringing back to the same initial position, of course your delta will become 0, isn't it? Of course your delta will become 0. Now suppose you are bringing back to the same initial position. If you are bringing back to the same initial position, if bringing back to initial position, what will happen? This delta will become 0, isn't it? So delta 1 minus delta 2, I can write it down as 0, whereas delta 1 is what? Alpha LT minus delta 2 PL by AE equals to 0. If you want to find out what is the value of P, of course you can get it. That P value will become nothing but, see, LL will get cancelled and you will get alpha T A E. That is the compressive force generated if you are going to restrain the bar. And the stress which is going to generate that stress, you can of course divide it by A and you will get the stress. Divide this force by cross-sectional area and you will get the stress. That is nothing but alpha TE. Right? Now solve this problem. A copper bar, yes, what you are asking, Santu, alpha having more value is compression or tension. Okay, that composite bar also need to be discussed. Can you solve this problem? A copper bar of 25 centimeter length is fixed by means of fixed support at its end. Support can yield. What is the meaning of yielding? Yielding means support may get, support may have some translation. Suppose. So a copper bar of 25 centimeter is fixed from both ends. It has a support at this location, and suppose the red support I'm talking about can yield, and it can yield by 0.01 centimeters. Means when you are going to increase the temperature here, when you are going to rise the temperature, this support, the red support, will come to this position maybe. The yielding, maximum yielding is, what is the value of yield? That is 0.01 centimeter. Support can move by 0.1 centimeter. Sorry, 0.01 centimeter. Right? If the temperature of bar is raised by 100 degrees centigrade, then the stress induced in the bar, he is asking. Suppose, first of all, he is saying that if you are rising the temperature by 100 degrees centigrade, same approach can be utilized. First of all, find out what is the free expansion. So if you will remove the support, what will happen? This bar will expand, isn't it? This bar will expand. If I am removing that right side support, this bar will get expand. The expansion value, maybe this is delta 1, which is nothing but your alpha LT. So delta 1, I can write it down simply. I can write it down. The delta 1, or maybe I'll write down here, delta 1, which is the free expansion. Then you are going to apply the force to bring it back to the position. Which position? At which position you will bring it back? You are going to bring it back to this position, because this is the yielding of the support. Support, after increment of your temperature for the bar, the support is going to move from position A to position B, and position B is the final position. So we are once again applying the force to bring the bar at the final position B. That is nothing but your delta 2. So this value delta 2, you are doing it by application of the force, right? So what is the compatibility condition you can write down? So delta 1 is your expansion, free expansion, minus delta 2, you are applying the force to bring back to the same position. Here in this position B must be equals to the yielding, that is 0.01. That's all. That's all. So delta 1 you can write it down. Delta 1 is nothing but your alpha LT minus delta 2 is nothing but PL by AE. PL by AE must be equals to 0.01 centimeter. 0.01 centimeter. LL will get cancelled, and P by A is your stress he's asking about. Alpha value you have given, it is here 20 10 to the minus 6. Then rise of temperature is 100 degrees centigrade, minus P by A I can write down as a stress. Here P by A I can consider it as a stress, this P by A, and divided by E. E value is you have 1 into 10 raised to 6 must be equals to 0.01. Now if you calculate from here the stress value, how much you'll get? You'll get around 16 into 10 square kg per centimeter square. Did you get that? Now sometimes how one will solve the tapered type of, if tapered type of bar you have, this is the one problem you have. The steel bar AB shown varies linearly in diameter. So you have a diameter here which is 25 mm, and you have a diameter here which is 50 mm. This is a tapered bar. It is fixed from both sides, and you are going to rise the temperature. Due to the rise of temperature, what is the amount of force which is going to be developed in this particular bar? Or maybe sometimes they can ask you what is the maximum stress or minimum stress in this bar. See, as you know that you have a tapered section of the bar, the stress will vary, isn't it? But the force will not at all vary. Force will be same throughout the bar. How you will find out the force? To find out the force, once again you will apply the same concept. First of all, you will go for the free expansion. What is the free expansion? Without support, what is the free expansion? So free expansion here will be alpha LT, where alpha is given as 12 into 10 to the power minus 6, and length of the bar is given as 500 mm, multiplied by temperature rise is 25 degrees centigrade. This is the free expansion you have. How much you'll get? 0.15 mm. Is it 0.15? This is the free expansion you have. Now this is your tapered section of the bar. Earlier, how you have calculated? See, once it will get expanded, you are going to compress it once again. Suppose you have tapered section of the bar, and for the tapered bar, if you are going to apply the force, what is the delta? See, earlier it was the cross-sectional area was not varying at all. Here the cross-sectional area is varying. That here you have some D1 dia, and at this location you have some D2 dia. What will be your deflection? What will be your deformation at this bar? For this bar, the deformation will not be same as what you have done for. See, when the cross-sectional area was not varying, the deformation was simply PL by AE. If you find out the circular one, you will see that A is nothing but PD square by 4E. Just I'll tell you how to remember that. It will become 4PL by pi D square E. From here, see, this is the normal one already you have remembered. For the constant cross-sectional area, you have a PL by AE. A already is cross-sectional area. If it is constant, D is pi D square by 4PL by pi D square E. Now, remember it whenever the cross-sectional area is changing or varying for the tapered section of the bar, 4PL by pi D1 D2E. That is the deformation of the bar here. This, see, earlier it was a same cross-sectional area. Here the deformation formula, so delta, need to be applied carefully. Finally, if you are bringing back to the same initial position, see, you have given the free expansion, then you are applying the force to bring back to the initial position. So still I'm writing down same delta equals to delta 1 minus delta 2, but this delta is 0. This delta 1 is your free expansion, which is alpha LT. I'll write down once again, minus this delta 2 is nothing but your 4PL by pi d1 d2 e. Did you get that? From here, you keep the values of all this alpha LT already we have calculated, then so it will become 0.15, that is 4PL 4P into length of the bar is given as 500 mm divided by pi into d1 is 25 mm and d2 is 50 mm. E value also is has been given, that is 2 into 10 is to 5, right, equals to 0.15. If you solve it from here, you'll get the p value, which is nothing but 58.9 kilonewton. 58.9 kilonewton. Right. Now, if someone will ask what is the maximum stress in this bar, the maximum stress can be calculated. See, you will be having stress at this location. So a force, constant force is there throughout the bar, which is 58.9 kilonewton. That force, if you divide with the least cross-sectional area, you will get the maximum stress. And if you divide it with the maximum cross-sectional area, you will get the minimum stress on the bar. That's all. That's all. Did you get that? So you can solve this type of problem in this way. This is the series we have started for your benefit, and please whenever it is there, you please try to watch the session. It will be very much helpful for your GATE examination. That's all from my side. Thank you everyone. Good night. See you.